Centre for Inquiry, Canada's premier venue for secular humanists, atheists, skeptics, and free thinkers.
Amanda Peet is an associate professor of physics at the University of Toronto and a fellow of Trinity College. She holds a Bachelor of Science honors from the University of Canterbury and a PhD from Stanford. Her awards include a Radcliffe Fellowship from Harvard University and a prestigious Alfred P. Sloan Foundation Research Fellowship. She's one of the string theorists interviewed in the three-part, very much acclaimed and popular Nova PBS documentary, Elegant Universe. Please help me welcome Professor Amanda Peet.
Thank you very much for the generous welcome, both from Justin and from everybody. Thank you for coming out on such a slushy, crappy winter evening to hear all about string theory. I'll do my best to be as entertaining as possible. The way that I'm going to structure this presentation is that I'm going to speak for maybe an hour, maybe a bit less than that. And I would ask that if you have questions, please note them down as we go through, perhaps on a little piece of paper or whatever you might have in your pocket. And then we can come back to ask afterwards. I'll take any and all science questions. If there are more philosophical questions, I'll also answer those once the science questions have been answered, as in the description of my talk that was sent out. One of the things, so questions after the talk if you can, unless there's like something that's just an incredible emergency and, you know, it has to be resolved within 2 seconds or else we can't continue, you know. Sometimes those two things do happen, but they tend to be rare. We ask people to try to afterwards keep their questions as short as possible so that as many people get a chance to ask as possible. So what I'll be doing is trying to alternate over here so that I can... This is the slide that has the most small type on it, and you are probably not going to be able to see it, but what I wanted to do was just to give you a sense of the range of topics that we will be talking about. Oh, you can... if you cared, that would be absolutely spectacular. What I want to do is to spend over 1/3 of the talk, probably almost a half of it, talking about string theory and unification and the reasons why we all came out for this talk. But in order to be able to describe to you how all that works, I need to set up two very important things I like to call twin pillars of 20th century physics, namely gravitational physics, which has to do with the Big Bang and cosmology, how the whole universe is evolving, and also has to do with some sexy things called black holes. I'll also talk about quantum physics, which instead of talking about macroscopic length scales is all about really small distance scales and the weird things that happen once you start peering down into that microscopic realm. In particular, I'll talk about subatomic particles and force messengers and particle colliders, quantum uncertainty, really sexy sounding stuff. And then I'll start talking about the reasons why physicists wanted to unify all the forces together. After all, it sounds like a pretty idea, but why bother? I mean, sometimes there's a pretty idea that's not awfully practical. So what were the practical reasons why physicists are trying to do this? And that will give me an entrance to introducing string theory. And there's plenty of things to say about string theory. Of course, I could talk about it for years. I do teach graduate courses on the subject and other things. So there's just a huge amount of information here. But what I'm going to do, instead of doing the usual thing when you give a talk, to say one thing and show something else on the screen. Because there's going to be quite a lot of information coming to you, and some of it may be unfamiliar because I imagine not all of you are physicists. So you'll see pretty much the same thing on the screen as I will be saying. And I did that on purpose, not to bore you, but to increase the probability that the information that you hear will stick in your mind. So what is the scope of string theory? After all, you know, what are we trying to do? How big is this ambition that the field has? Well, for much of the 20th, one point I really want to make is for much of the 20th century, physicists classified themselves as either theorists or experimentalists. They either measured stuff in the lab or modeled stuff with mathematics. A few, like Richard Feynman, managed to do both in a really excellent way. They became more rare as physics became more of a developed discipline because all the easy problems got picked off. In the 21st century, it's not a two-way thing between theory and experiment anymore. It's a three-way between measurement, modeling, and simulation on a computer. And the reason why computers have waited until now to come into the equation is simply that previously they weren't powerful enough to be really, really useful in pushing the frontiers of research. So what do string theorists want to do? Well, we're part of a crew within physics called the high energy physicists, and it's not because we're kind of fidgety and moving around and having high energy all the time. It's because of the subject that we study. It has to do with high energy physics or extreme physics, the kind of stuff you would find bashing particles together inside a collider at the Big Bang deep inside a black hole. So if you like, you can think of high energy physicists as being kind of like extreme athletes in physics. So what do we want to do? We want to explain the structure and origin of particles and forces, and even space-time, right from the very smallest imaginable subatomic scales out to the very edges of the cosmos. And in plainer language, what we're daring to do is to try to figure out the universe's operating system. We want to make sure that we understand all the rules of how it works over those, huge dynamic range. And if people are familiar with the terminology, that corresponds to about 60 orders of magnitude, or 60 powers of 10, in terms of the dynamic range that we're trying to cover. It's just humongous. So that's why people call us arrogant. So let's get started. I mean, how, after all, do we learn about the universe? Well, one of the things that astronomers have learned how to do to figure out the history of the cosmos, we don't have time machines, we don't have Star Trek Enterprise at a disposal. What we use is the fact that light, even though it travels very fast, it still takes a finite time to get from A to B. So to illustrate this, just imagine seeing a firework. You will see it go pop before you hear it go bang. And the reason for that, of course, is that the speed of light is much faster than the speed of sound. So the light gets to your eyes before the bang gets to your ears. But the time lag even for light is finite. The sun, for example, is 150 million kilometers away from here. And light, even though it's extremely quick, still takes 8 minutes and 20 seconds to get from the surface of the sun to my eyeballs. So if I see a little bit of sunlight right now, what I am seeing is the sun as it was 8 minutes and 20 seconds ago. Similarly, if I got some light from a star that was 4 light years away, that would mean when it reaches my eye, it had been traveling for 4 years to get here. So when I see it, it will tell me about how the star looked 4 years ago. So this is the time machine that astronomers use to look back into the deep history of the universe. Special relativity's bedrock principles are not violated. Light speed is the same in all frames of reference. There's no Star Trek time travel. There's no causality paradoxes, and no information can ever go faster than light. But what we're using is the fact that the speed of light isn't infinite. That's an experimental fact, and it helps us. Now, here's the rub. If you're wanting to look very far back in time, you've got to look for light from very far away stars. But faraway starlight, could you move it back, is fainter because it spreads out uniformly in all directions from the source and not just in our direction. So what astronomers have to do is build exquisitely sensitive telescopes, and they have done. So one thing that you may already know is that light is a part of a giant thing called the electromagnetic spectrum. Visible light, the stuff that you and I can see with our eyes, ultraviolet light, infrared, radio, radar, X-rays, microwaves, gamma rays, TV, they're all just different forms of electromagnetic radiation. And physicists say the terminology that they're made up of little particles called photons. Photons are massless. They always go at the speed of light. Well, that's good because we said that they were the particles of light. They can only go at light speed. So they can't speed up and they can't slow down. But they can change their heading, the direction they're moving in, and they can change how much energy they have. The energy of a photon, a little particle of light, is proportional to the frequency. So redder photons have a longer wavelength and less energy per photon. The bluer ones have more energy, more of a kick per little particle of light. Now, energy for a particle, or its wavelength equivalently, depends on your reference frame. You know when you hear an ambulance going down the street and you hear the Doppler effect? As it's coming towards you, it goes nee-ner, nee-ner, nee-ner. You know, the pitch raises, and then as it goes away from you, the pitch drops. Well, there's a similar but not identical phenomenon for light, which is when the source for the light is moving towards you, it bunches up the wavelength and it makes it bluer. That's called blue shift. Similarly, if the source is moving away from you, then it makes stretches out the wavelength, makes it longer, and makes the light redder. That's called redshift. So looking at starlight and knowing something about the kind of light that's emitted from stars allows us to tell about the state of motion of those stars. So light was very, very important to Einstein's new theory of general relativity, which was invented about a century ago. So we're talking about really century-old physics here. But before Einstein had even put pen to paper to try to make a beautiful new theory of gravity, 300 years earlier, Newton had made a very big insight, which people call the Law of Universal Gravitation. And he said, well, the very same gravity that drives the motions of celestial bodies keeps baseballs here on Earth. It's just the same gravity. It's not a different gravity for the heavens. Or in a different gravity for what happens on Earth. It's just the very same gravity. And gravity, according to Newton's theory, which I like to call gravity 1.0, you know, like Webb 1.0, Webb 2.0, well, Newton's theory of gravity 1.0 responded to mass. So if you had mass, you would gravitate. So for instance, picking me and any person in this room, we feel a very weak gravitational attractive force between us. Thank goodness that the gravity is so weak, otherwise the strong force would, you know, the gravity would just make us all in a group hug in the pile in the middle of the room together. Newton's theory of gravity, while it's not correct, wasn't really that wrong for things that move slowly and so forth. The accuracy of Newton's theory is perfectly fine for landing astronauts on the moon. You don't need any of the fancy mathematics of Einstein's general relativity to be able to do that. But what Einstein did is he started with Newton's gravity, which was a great sort of approximation, but he had a suspicion it wasn't, you know, correct in full detail. And he added the ideas of special relativity, that you can't go faster than light. And he figured out a consistent combination of those ideas called general relativity. So that's just basically relativity when you add gravity together. And gravity became a thing called space-time, which was a geometrical concept, as compared to Newton's idea of a gravitational force that would just reach out and grab. And Einstein's equations will correct Newton's one when gravity is strong, like when you've got a situation with a black hole, or when speed is high. And the only place I can think of where every one of you has already met something that uses Einstein's general relativity every day is if you've used a GPS device. Those little satellites that have the very precise atomic timekeeping things on them are flying in orbit around the Earth at a significant speed, and the fact that they're moving at some fraction of the speed of light is important. Similarly, because the satellites are higher up in the gravitational field of Earth, they don't feel quite such a strong gravity tug as we do here, because we're closer. That difference leads to also a change in the clocks. And if your GPS device didn't take into account general relativity corrections and special relativity corrections, you would be lost by several kilometers per day. So that's the only example I can think of. Anyway, next page, please. So one major discovery in physics that you may not be aware of is that was made, let's see, 80 years ago. Our universe is actually expanding. Other stars are on average racing away from us. Hubble, who made this discovery, codified his discovery in a law, and he found that it was even more puzzling than that further away light sources seem to move away from us faster. And they worked it out because of that blue shift, red shift thing I talked about. They found that the velocity that the star was moving away from us was proportional to how far away it was, which is very puzzling. I mean, how could it be that everybody's running away from us? Do we smell or something? So what then people realized is, oh my goodness, using Einstein's new space-time ideas, that if the fabric of space-time is expanding, then you take any two little stars or galaxies that are next to one another, and if the fabric of space-time expands, like somebody's blowing up a balloon, then any two stars will get further away. And the further away they were when you started, the faster they'll be going away from each other. And from information like this, looking at starlight, essentially in a very clever way, people have figured out that the age of the universe since the Big Bang is about 13.7 billion years. That's about how old we think the universe is, plus or minus, 100 million years or so. So you might ask, how would astronomers and physicists figure this stuff out? I mean, how can anybody stand there seriously and say, oh, well, the universe is expanding? Because they haven't reached out and touched it. They haven't measured it with a tape measure or actually been able to feel it with their fingers. But that's something that happens to physical scientists quite a lot nowadays. There are phenomena that are accessible directly, things that we can use our fingers for, maybe things that we can use lasers to play with, but many others are not. We have to use rather indirect methods to be able to see or poke them. In the case of these stars, we look at the light that comes from them and use that information to tell about what they're doing. Now, some of you may know that there's a current hypothesis that this expansion of the universe can be explained by having had a big explosion right at the beginning called the Big Bang. And there is actually some radiation out there in the universe everywhere that's left behind from the Big Bang. This is called the Cosmic Microwave Background Radiation, or the CMBR. And I don't know how many of you are old enough to ever watch one of those old vacuum tube televisions? The ones that if you would tune between the channels, you would get snow on the screen? Well, about 10% of that is actually radiation left over from the Big Bang. It's that cosmic microwave background radiation. And Penzias and Wilson discovered this in 1965. They happened to have been, I think, looking for something else, and they found, when they pointed their sensitive detector out into the sky, they found this messing up their results. And then they suddenly realized, oh my goodness, we've discovered radiation echoes of the Big Bang. Gosh darn. So it's electromagnetic radiation left over from the Big Bang. When the early universe was, much younger, it was a lot smaller because it hadn't expanded so much yet. And the radiation back then was a lot hotter. The Big Bang was an extremely violent cataclysm. But nowadays, because the universe is stretched out so far, and because the stretching of the fabric of space stretched out the wavelengths of those photons, they are now only correspond to a temperature of about 3 degrees above absolute zero, and it's in the microwave. And that's why we call it the cosmic microwave background radiation. If we wait another few billion years into the future, it'll have an even longer wavelength, but hopefully none of us will be around to see that. So another thing that you can do by looking at stars and so forth is to weigh the cosmos. You can work out a composition of the universe using CMBR. You can look at supernovas going bang, look at large-scale structure of galaxies, and do experiments in space and on Earth. And there's a really amazing thing that you discover if you look at the pie chart for the composition of the universe. And that is that heavy elements like us, stuff like carbon and oxygen and good stuff like that, makes up about only 0.03% of the universe. We are very rare. Little subatomic particles called neutrinos make up a little bit. Stars, which are undergoing nuclear fusion, make up about 0.5%. Just random free hydrogen and helium gas, which were made in the Big Bang, about 4% of the matter. So all of this is stuff we understand. People teach about it on the periodic table in science class. But then there's about 1/4 of the stuff in the universe called dark matter, which we think is made of stuff, but it doesn't shine, so we call it dark. How imaginative. Yeah, it's really nothing more than that. Dark matter is just stuff made of subatomic particles that have mass, and we call it dark because it doesn't shine. But 70%, this huge big purple part of the pie chart of the universe, is made up of stuff that just has energy, no mass, and it's dark. It doesn't shine. So it's really, really puzzling. And it was a terrible shock for us theoretical physicists to discover when they went and actually weighed the universe, that most of it, by far the majority of it, 95% of the universe is made of stuff we have no idea what it is. So if anybody's thinking of a subject to go and study, well, this is somewhere where there's a lot of room for new ideas. Another thing you can discover by weighing the universe, looking at the radiation that's left over, all these things, you can discover that the expansion of the universe is not only expanding, it's accelerating expansion. So it's expanding faster and faster with time. If you decide to try to work backwards and see what that could have come from, you take Einstein's equations back to the beginning, and it signals what's called a curvature singularity. This is a nasty place at which the space-time is so strongly curved that it just, becomes unmanageable. The theory, literally, Einstein's beautiful theory, this gravity 2.0 that everybody thought was so fantastic, it basically just falls over on its face and fails to tell us anything about the physics of the Big Bang. So that's one reason. All the story about cosmology in the universe is one reason why we dig deeply to try to understand the nature of gravity at short distance, and that's part of the motivation for string theory. Another motivation is black holes. I will speed on... black holes. Next... Yeah, I guess that's the right page. A black hole is something which is, the gravity is so strong that you can't escape. Various of us have seen pictures on the TV of a space shuttle launching off into space, and it needs strong rocket engines to be able to escape the gravity pull of the Earth. And the heavier a body is, the harder it is to get away from it, because it pulls harder. And also, if you're closer to the body, then it's harder to escape because you're feeling a stronger force. So the escape speed from a body depends on the mass and how close you are. It rises to light speed at a place called the event horizon. So if there is a thing which has a very strong gravity and it's got a thing called an event horizon, then if you fall through that place, it's the place of no return. Because if you would try to get out again, you'd need to be able to go faster than light. And nobody can go faster than light. Light is kind of like the speed cop that says 186,000 miles per second. It's not only a good idea, it's the law. You know, those silly T-shirts with a picture of Einstein on them. At any rate, it's really bad because not only can you not go faster than light, you can't even send signals out to say, help, help, I fell into a black hole, come and rescue me. So, you know, you're screwed. By the way, an object is called a black hole only if it's dense enough to be contained within its own event horizon. Just to give you an idea, if you took the mass of Earth, like the whole planet that we live on, with all the rocks and everything, and you asked how big would the event horizon be for something of that size, you discover that it would be about the size of a ping pong ball. So if the Earth were to be a black hole, it would have to be all scrunched inside something the size of a ping pong ball. And it isn't, so we can rest easy that the Earth is not a black hole. Neither is our sun. But if you have a very big star that's quite a bit heavier than our own star, the sun, then after it uses up all of its nuclear fuel, like burns all the hydrogen, then it burns all the helium, and then it burns all everything else it's got, and then it runs out of gas, literally, then there's nothing pushing out with the pressure anymore because of the nuclear fusion, and the only thing happening to that dying star is that gravity is pulling in on it. And when it really super collapses and there's so much mass, then you get left behind with something that's called a black hole. There are black holes out in the universe that have masses of 10, 100 solar masses, where solar mass is the mass of the sun. There are also, at the center of every galaxy, 90% of every galaxy, so most of the galaxies in the universe have a supermassive black hole at the center. And those things have a mass of about between 1 million and 1 billion times the mass of the sun. There's this is supposed to be a Lego Stephen Hawking. When I just came across this picture on the internet, I knew I was going to use it multiple times, so apologies for that. I have, however, met the guy and talked to him, and he's a very, very courageous and amazing individual. So Hawking discovered, by looking very deeply into the structure of space-time and quantum physics, discovered that actually something does come out of a black hole. Not very much, but something very weeny. And a black hole actually has a temperature, and it radiates like a hot body, which is similar to what would happen if you looked at a red-hot coal and tried to look at the radiation that came out of that. The Hawking temperature depends only on the black hole mass and a couple of other things, and it's very, very low for astrophysical black holes. If you had a black hole that had the mass of the sun, it would only radiate with this Hawking radiation, this thing for which Stephen Hawking is so incredibly famous, at about 10 to the minus 28 watts. So that means you would have to have, like a billion of these things to be equivalent to a 1-watt light bulb. That's a lot colder than the cosmic microwave background radiation, and so you never see Hawking radiation for big astrophysical black holes. But where it's important is in the physics of very small ones that might have been made in the Big Bang or inside particle colliders, and then you really have to worry about it. Now, there's something to do with black holes that people got very puzzled by and still hasn't really been solved yet, but string theory has some proposals about, contributions to make to that puzzle, which is the problem that let's consider a black hole to be just an ordinary thing. Suppose we chuck some stuff in, like we chuck a 10-kilogram fish into the black hole, and then we wait for some Hawking radiation to come out. We could compare that to doing a different thought experiment where we chuck, instead of a 10-kilogram fish, we chuck a 10-kilogram textbook, preferably a physics textbook, into the black hole. And then we wait for the Hawking radiation to come out. The problem is that the Hawking radiation only knows about the mass that went in. It doesn't know that it was a fish or a textbook. And so that's called the black hole information problem, that if you chuck stuff into black holes, some of the information doesn't come out. And physicists get very upset when information goes missing. It means we failed in our job to keep track of everything and to understand stuff. If all of a sudden we discover an animal in our description of the world that just eats information, gobbles it up and it's gone, vanished, that gives rise to a giant puzzle. What happened to the missing stuff? Where did it go? Is it somewhere? Are we ever going to get it out again? Those kinds of puzzles. Next slide, please. There's something also that's even worse if you happen to keep falling into a black hole. And there's this place called the event horizon, which is your point of no return. But in the very center of a black hole, there's an even more violent place called a singularity. This is a place where the curvature of space-time becomes infinite. This means that because the curvature of space-time is what drives tidal forces, you know why we have tides on the Earth? You know, like ocean stuff going up and down and up and down. Well, that's because as the world is spinning around, it feels the gravity from the sun and from the moon, and the gravitational pull from the moon helps to encourage the water that's closer to the moon to go a bit closer, and so forth. So this business of tidal forces is everywhere in the universe. It explains our tides, it explains a whole lot of other things. But one of the problems is that if the curvature of space-time becomes infinite, so do tidal forces. So if we chucked one of you into the black hole, by the time you got to the singularity, you would be completely spaghettified. You would have been pulled apart, squeezed, stretched, just, atomized, and then all the atoms would get destroyed, and, you would be so dead. So please don't fall into a black hole. But don't worry, there aren't any within light years of here, so there's no probability that any of us will get gobbled up by one of these violent things. The only problem with the black hole singularity is really that we don't know what to do there. Einstein's beautiful gravity 2.0 theory runs out of ideas about what happens there. So there's two places in gravity physics where Einstein's beautiful theory is a terrible failure. One is the Big Bang, and the other one is the very heart of a black hole. So those are two very big signals that there's something that we don't understand about gravity physics. Next slide, please. So this is a very busy slide, but let me just pick out the important things. In order to understand what happens at the very center of a black hole in a very small place with very strong gravity, but also understand what happens at the Big Bang, that point of origin of the explosion that expanded out to become our expanding universe. In order to understand the physics, we're going to have to talk about the quantum realm. We're going to have to talk about the physics of the macroscopic, but also the physics of the microscopic to understand what to do at black hole and Big Bang singularities. So quantum mechanics is a subject that was developed starting in the 1920s and is a topic we teach several courses on to our physics undergraduates before they get out the door, our majors and specialists at least. Quantum mechanics has two main cornerstones. One is that energy is not a continuous thing. It only comes in lumps. They're called quanta, or quantum for the singular. Objects like electrons have both wave-like behavior and particle-like behavior. So they can behave like little marbles. That's called having particle-like behavior. And they can also have wave-like behavior like water waves. And which behavior you see depends on how you do the experiment. I can talk in detail and question about that if you want. But I like to encourage people to think of things like electrons or Professor Peet's or whatever we're talking about as wavicles. Don't call them particles, call them wavicles. They have wavy behavior and they have particle behavior. So using a word that's a combination, I just like to call them wavicles. That's the same idea as a quantum. It's just a little packet of energy, and it has wave-like behavior like interference and diffraction being confirmed in the laboratory. And that's just like when you have water waves. Suppose that you throw a stone into a pond, and at the same time somebody else throws a stone into a pond a little further away. Those waves will eventually interfere with each other and create pretty patterns. The same thing happens with things like electrons and so forth. Incidentally, the story that energy only comes in discrete lumps is called the quantum hypothesis, and Einstein won the Nobel Prize for explaining something called the photoelectric effect, which depends on the fact that energy only comes in discrete lumps. It's the reason why cell phones can't cause DNA damage. One of the things that people have discovered, and this comes back to our exploration of the universe by looking for light, is that energy levels, possible energies that you could have if you're an electron whizzing around an atomic nucleus, they're discrete. That's related to the fact that in quantum mechanics, energy can't be anything, it comes in lumps. So there are only certain possible energies for an electron to have if it's in an atom. And what that results is, this is just supposed to be a picture with different possible orbits of electrons around the central nucleus here. And if you happen to be in a outer state and you fell down into an inner one, then you would have to emit some energy. And that comes out in the form of a lump called a photon, and it has a particular frequency. Because you're changing energy levels, you emit a photon with the difference in the energy. These are called spectral lines. And so if you looked at a bunch of hydrogen gas and tried to find out what does it emit, what comes out if you excite a hydrogen gas and then you let it relax down and see what happens, what radiation does it emit, and you discover lines. something in the red, something in the cyan, blue, violet, and then there are other ones either side. This is the reason why astronomers can figure out the state of motion of stars, because the hydrogen on Earth is the very same hydrogen that's occurring in a cloud in a galaxy 100 light years away. And the emission is the same from the hydrogen atom here on Earth as it is out there, but if it's in relative motion, I will see these lines shifted. They'll be blue shifted if it's moving towards us, they'll be red shifted if they're moving away. So quantum mechanics was absolutely essential to the discovery that the universe is expanding. Please go ahead. Now, let's talk a little bit about subatomic physics. Various of you may know that, of course, there's a nucleus in the middle, and there are protons and neutrons inside, and then there are electrons that are orbiting around in a fuzzy cloud sort of situation. Atomic size is about 0.1 nanometers, so that's a tenth of a billionth of a meter in size. So they're really small, and we can't touch them with our fingers because we're too big and clumsy. Inside the atomic nuclei, there are protons and neutrons. The number of protons tells you which atom it is, and the number of neutrons tells you which isotope you've got. And people had discovered also that neutrons and protons are not elementary. They're composite. They have three little nuggets inside them called quarks. And you can make protons and neutrons from what are called up and down quarks. Up, up, down is called a proton, and up, down, down is called a neutron. And there's a lot more games you can play with quarks to make lots of different kinds of subatomic particles. Now, how do people tell particles apart? One of the things you might wonder is if you were doing a particle experiment, how could you tell an electron, say, from a neutron? How would you determine which is which? Well, one of the very first things you'd want to do in order to come up with a sensible taxonomy scheme for particles is to use labels that would be the same in any frame of reference. For example, if I'm whizzing by in my spaceship at half the speed of light, I want to be able to agree that that's an electron. Despite my state of motion, we will want the very same electron to be identifiable. So what people do is to use a principle called symmetry in physics, and discovered that there's only three properties of particles that are the same in all frames of reference. And so they're the way that we classify particles. The first one is the mass, how much mass it's got, how heavy it is. The second one is something called the spin, which is an intrinsic amount of angular momentum. And the third thing is the charge. So for instance, we know an electron because it has a negative charge, and that responds to magnetic fields in our detector. There are two types. The mass can be anything for a subatomic particle. The spin can only be integer or half integer. The difference is bosons and fermions. They have different names. All fermions, including electrons which have a spin a half, obey something called the Pauli exclusion principle. This is a very important part of quantum mechanics that says that no two fermions, like no two electrons, can be in the same quantum state at the same time. And this Pauli principle is responsible for the fact that larger atoms are actually physically larger. Okay, next slide. I want to also, apart from telling you about what subatomic particles are made of, we need to talk about forces. As you may know, there are four forces in the universe. One is gravity, that keeps all your bums on the seats. Another one is electromagnetism, that makes the lights go. There's also the strong nuclear force, which holds the atomic nucleus together, and there's the weak nuclear force that causes radioactivity. But how do we think of this in terms of particle physics? Anybody been skating recently on ice, or watching hockey players on TV or anything? I watched the game where they flattened the Russians. That was really awesome. Sorry. What I now want to do is use an analogy of ice skaters to show you how particle physicists think about force. So what I'm going to do is take this chap in the red scarf here and imagine that he and I are on the ice together. And we start out just standing stationary. I have a heavy ball. I mean, it was boring, but you know, we're physicists. What I'm going to do now is chuck the ball to him. Now, you all know about the phenomenon of recoil. Like if you've ever fired a gun, you know that when it goes bang, the bullet goes one way and the gun goes the other way. And that's just a principle of conservation of momentum, but you can just think of it like recoil. Well, because of recoil, when I chuck the ball to him, I'm going to move in the other direction than the ball. I'm going to start moving away. Now, what's going to happen when he catches the ball? Because of recoil, there was some momentum going towards him, he's going to go backwards when he catches the ball. So he's going to start moving away from me. Next, what he's going to do is chuck the ball back to me. And because of recoil, after he's chucked the ball, he's going even faster. So now I catch the ball, and because of the momentum, the recoil, I go further away. And if we keep rinsing and repeating, chucking the ball back and forth, we're repelling from each other. We're moving away from each other, and we both feel the same strength of the force. So that's an analogy for how to think about force as transmitted by messenger particles. In this analogy, he is playing a role of an electron, I'm playing a role of an electron, and the photon, which is the transmitter of electromagnetic, in particular for electric repulsion, the little photon plays the role of the ball that's being chucked between the two of us. Next slide. So force messenger particles are called the photon, that transmits the electromagnetic force. The graviton is the hypothesized messenger for the gravity force. I say hypothesized because we haven't yet directly detected it in a detector, although LIGO and other experiments are looking. But there's so much indirect evidence that everybody is convinced that it is there, but we would really, really, really like to see it, for real in a detector so we can say we really understand this shit. Pardon me. There are 8 gluons that help to transmit the strong force that holds atomic nuclei together. There are particles called the W's and Z's, which transmit the weak nuclear force. And there's lots of information to be known about forces. In particular, the gravity is the weakest force in our universe today. The strong nuclear force is the strongest, and the other 2 forces are somewhere in between. Next slide. So there's a Lego set that we can then put together after doing all these investigations, which says that you can build any particle that we've yet discovered in the lab by using 6 flavors of quark Lego. They have names like up, down, charm, strange, top and bottom. There are 6 flavors of lepton Lego. These are names for electrons and their heavier cousins, the mu and the tau, along with their little friends called neutrinos. And with quarks and leptons, you can make everything that we've ever seen in the lab, as long as you bind them together and have the force particles doing the messengering. So the photon does the messengering for electromagnetism, the gluons do the messengering for the strong force, and the W's and Z's are responsible for the weak nuclear force of radioactive decay. Physicists are, by the way, in hot pursuit of a particle called the Higgs, which is the one unexplained, biggest unexplained feature of our little Lego set. And that is a mechanism which gives mass to a bunch of particles in the Standard Model. Anyway, next slide. The current frontier of where people are at with trying to understand all this is there are 2 places. Particle colliders is another word for them is atom smashers, where you use as much technology as you can pay for, as you can convince world governments to spend, to whiz things around in circles and counter-rotating circles and then bash them together at unimaginable energies. The Tevatron at Fermilab is, because it's in America, it has 4 miles in diameter. The current machine, which is going to gear up and start beating the pants off this in a few months, has a European distance of 27 kilometers in diameter. This one is near Chicago, that one is near Geneva. This one is running at a particular energy called 2 TeV, and this one is gearing up to be 3.5 times that. So these are the current world beaters for how things are going. And just to give you a sense, this is Lake Geneva here. These are the mountains, and this is how big this damn thing is. It's underground, between 45 and 100 meters or so underground, and it just has the most stupendous amount of technology inside, including the biggest reserve of liquid helium in the world. When it's cooled down, it's colder than outer space. Colder than that cosmic microwave echo radiation left over from the Big Bang. Next slide. So let me tell you something about quantum physics. You may have heard of something called the Heisenberg uncertainty principle. It's very specific. It limits precision of specific pairs of physical observables. But here's the best example of the Heisenberg uncertainty principle, energy and time. The essential idea is that if you do an energy crime, if you get away with it quickly enough, it's okay. Quantum physics also introduces some random jitter about things. You can never turn it off, even at absolute 0. So there's an average behavior for quantum systems, which is like my behavior. But there's jittering about the average. So things are just a little uncertain. There's a rough average of where I'm moving, but there's a lot of sort of variation on top of that. The reason why you don't see that happening, that quantum jitter happening to me right now, is that I'm far too big. And the quantum jitter for me is measurable, but it's so small that you would need a particle accelerator to see it. So for macroscopic objects, all this quantum jitter is completely irrelevant, but it's very important for very small things. Let me just whiz through this because I'm, losing some time. The effect of let me just skip it. Go to the next one, please. One of the things that you discover if you poke very deeply into the structure of force in particular is that you discover that things that you thought were constant, like things that characterize the strength of the electric charge on an electron, they're actually not constant. Somebody lied to you when they told you all their life that the electric charge on an electron was just fixed. It was -1 in whatever units. Well, they lied. In fact, if you peer down very deeply into the structure of the electron, you discover that the closer in you can dig with your higher energy particles, the more charge you see. And that's called the running of the couplings. And when people turned on this giant particle accelerator that used to be in the same tunnels as the LHC is going to be in near Geneva, they discovered that if you look at how the electromagnetic force starts running, if you crank up the energy, look at how the weak force starts changing, look at how the strong force starts changing, then you get a hint that perhaps up at some very high energy scale, they'll all merge to have the same strength. This is the experimental motivation for the idea of unification. The part of the equation that we know is this part. We make a guess about what happens up there at very, very high energies that we can't currently make in the lab by just extrapolating what we've seen. That, of course, is a giant assumption, and there could be any number of things that change that on the way. But that's one of the motivations for why physicists wanted to unify stuff. So now onto the very interesting thing. Let's skip this. Now I want to get to the most important slide in the whole talk. So if somebody's fallen asleep because there's no air movement in here and it's getting extremely hot, perhaps we could actually open a back door so that there could be some air movement. It's getting extremely stuffy and people are falling asleep. Let's look at the reason why you need string theory. And this is the problem, that if you take these beautiful twin pillars of 20th century physics, one of them is gravity with all the stuff about cosmology, the Big Bang, black holes, and then you take the other pillar of 20th century physics, which is quantum physics, which governs all condensed matter systems. It's the reason why you've got a cell phone. It's the reason why your computer works. If nobody had bothered to fart around and understand quantum mechanics back in the 1920s and 30s, none of us would have these technological devices. So theoretical physicists thought, well, hell, why don't we try to just put them together? We've got this beautiful gravitational theory of Einstein's for the macroscopic world, and we have this beautiful thing called quantum mechanics to describe the microscopic world. Let's just put them together. And what you discover if you try to do that is that they're like incompatible couple who just can't get along. And one of the ways that a physicist goes about quantifying this is to ask, well, let's just pretend that Einstein's theory is a great quantum mechanics theory, and we'll compute the probability for gravitons scattering off one another. A graviton is just the particle that transmits the gravitational force. What you discover if you calculate the probability for graviton scattering, you discover it grows with energy, like the square of the energy. So if you would double the energy, you would 4 times the probability. If you would triple it, you would make it 9 times bigger. The problem with this is that at very low energies it's just fine, but at very high energies, eventually the probability will exceed 100%. Oops. This is about as bad a mistake as writing 1 = 0 in a math class. So the problem is that the probability for gravitons to scatter off one another becomes extremely large at high energy, and Einstein's theory just falls flat on its face. So if you try to ask, we know that if you have a probability, it needs to be somewhere between 0 and 100%. We shouldn't have -5% probability, and we shouldn't have plus 250%. We should have, between 0 and 100%. So that's exactly the problem of what goes wrong when you try to combine general relativity and quantum mechanics. So while general relativity is a mighty fine classical theory of gravity, it falls flat on its face when you try to apply it to the microscopic world, the world of quantum physics. So what we're going to seek is a new gravity theory that's better than gravity 2.0, so we're going to call it gravity 3.0, which is going to incorporate Einstein's beautiful ideas about space-time, and it has to incorporate quantum physics. So we've got these beautiful twin pillars, pretending everything was made of subatomic particles, like in the particle zoo slide, isn't good enough. We have to go to a bigger idea to be able to marry together quantum mechanics and general relativity. So one of the other things that string theory can do for you, other than be a gravity 3.0 theory that consistently combines quantum mechanics and general relativity, is that it also unifies all the 4 forces together. And this is something that Einstein dreamed of doing his whole life. He wanted to unify electromagnetism and gravity together. They both move at the speed of light. Gravitons move at the speed of light, so do photons. And he thought there must be some unified way of describing these two things in the same breath. And he sought that for his whole life. Never made it. unfortunately. I think if he had seen string theory, he probably would have been pretty excited about it. But, who knows? That's just a hypothetical. He disliked quantum mechanics. That might be one of the reasons why he failed in his quest. But he also ignored the nuclear interactions. The fact that he was only focusing on 2 of them is one of the major reasons why he missed this idea. So open string theory, a theory of little strings, these are not like cat string, in the sense that they're much smaller and they're fundamental Legos out of which we make everything. Open string theory was actually first invented to try to explain the strong nuclear force. They got close. In fact, my PhD thesis advisor, Lenny Susskind, was one of the first people to discover this, that you could just about explain aspects of the strong nuclear force by using relativistic open string theory. But there was a fatal flaw in the theory that they didn't discover for a little while, which was inside this story, there was a little subatomic particle that had no mass and had spin 2. It was only several years later that people realized this is the graviton. This is the particle that transmits the gravitational force. So what used to be a bug in this theory made it a terrible, awful theory for describing the strong force and got it thrown in the dustbin of history. When people realized that string theory had gravity in it, that was when people realized that it would unify gravity, electromagnetism, and the nuclear forces together. Moreover, and it would unify gravity and quantum mechanics. So what is this theory called gravity 3.0? Well, you make everything out of little subatomic strings. The Legos are tiny one-dimensional strands of energy, and this is just a picture of what it would look like if this is time and the across direction is space. If we had a little vibrating open string, as it moved through space-time, it would sweep out a sort of a wobbly strip. If we had a closed string, like a rubber band, as it moves through space-time, it would make a tube. And those things are called world sheets, and you can work out the dynamics of strings. There are different modes of oscillation of strings. When you have a guitar string, sorry, I'm going to try to play the guitar now, but if you try to play the guitar string, if you just pluck it, it plays the fundamental note. Then you can by putting your fingers on the frets, you can excite different modes of oscillation of that very same string. You can make different musical notes starting from one string. For example, if you're a violinist, you can hopefully play the entire air on G string while not moving off the G string of your violin. I wish I hadn't said that. So for the little relativistic strings that are the Legos of the entire universe, you can excite the fundamental, or you can excite the overtones. Of course, exciting the overtones cost more energy, so in general, if you have a really lean energy budget, then you're only going to be exciting the fundamentals. Different oscillation modes possess different mass, spin, and force charges, and they're interpreted as different subatomic particles. So all the different possible vibration modes of the string represent different subatomic particles. So this is a very, very big idea. It says, if you're willing to accept the idea that the indivisible units that are the Legos that are make up everything in the universe, if you're willing to entertain the idea that those might be strings, one-dimensional objects instead of points which have no substructure, subatomic particles, if you're willing to accept that things are made of strings, you can find all of the subatomic particles that are out there in nature and more besides. So it's a very economical idea once you've, got used to the idea that the Legos might not be point-like particles. And keep it on the same page, please. This is the most important page in the whole talk. The most amazing fact about string theory, which impresses people only in hindsight because people discovered gravity before they discovered string theory, but in a fictitious universe where we had theoretically discovered string theory and played around with it, we would have predicted gravity for you. So in fact, just saying that everything is made of little relativistic strings is enough to come out with quantum gravity, a consistent quantum theory of gravity, which reduces back to Einstein's theory in the macroscopic regime, but is changed in the microscopic quantum regime. So we're not messing with Newton's theory. When things are big and slow and everything, that's just fine. We're not modifying that. We're not even messing with Einstein's theory until you get down to very short distances. So we're matching on with what was already known. We're standing on the shoulders of previous discoveries. We're not saying that Newton's theory was totally wrong. Einstein's theory was totally wrong. String theory is totally right. In science, there's always a hierarchy of wrong. Well, for example, the Earth is flat. is a very good approximation if you only ever move about 1 kilometre. But if you want to go exploring the oceans, then it's a much better approximation to say that the world is round. In fact, it's not perfectly round. It's more like a squashed sphere because of the rotation of the Earth makes it fatter at the equator and flatter at the poles and fatter at the equator. Similarly, with gravity, Newton's theory is a perfectly good one in approximation, and then Einstein's is a better approximation, and we're saying that string theory is an even better approximation still. And the reason why it all works is that the fundamental, that ground state of oscillation of an open string is massless spin 1 gauge boson, and that's just a fancy theoretical physicist word for photons and gluons and W bosons. So you can make photons, gluons, and W bosons, 3 out of the 4 forces, out of little open strings. The ground state, the lowest musical note that you can make with a closed string has 0 mass and spin 2, and that's called the graviton. And this is how string theory unifies the gauge forces, the 3 forces that we already knew about in the standard model, with gravity. Because you have open strings, the lowest mode of oscillation of which is all those things that we just discussed, and you have closed strings, the lowest oscillation mode of which is the gravity theory, the graviton. Okay, finally we can move on to the next slide. We're almost finished. Now, one of the things that you may wonder is, how is this gravity theory that I've just talked about, this beautiful string theory animal, which says everybody's made of stringy Legos, how is that better than what we had before? In particular, how does it solve the problem of trying to understand what happens at the very point of the black hole singularity or the very point of the Big Bang? How do we understand the extreme physics of gravity in that situation? Now, you recall our little ice skater analogy for exchanging a little ball that was like the transmission of force? Well, in string theory, instead of having point particles being transmitted, we're chucking strings between us because we're just replacing particles with strings. So if we were to do this ice skater analogy with string theory, we would just be exchanging a little string between us, and each of us would be a string. So it's all about string. Not only the matter particles that make up stuff, but also the force messenger particles that make up the transmission of force, they're all included under this rubric of string theory. So it's a very bold idea, and it's very economical once you've gotten over the terrible shock of saying that everything's made out of little strings instead of little particles. So why is string theory so much better behaved? Why does it work as a theory of quantum gravity when Einstein's theory doesn't? Well, when we had the exchange of that little ball between us, that was happening at a particular point. There was a particular point in space and a particular point in time when you caught the ball. There was also an explicit, well-defined place in space and point in time when you threw the ball back to me. And in Feynman diagrams, which are the part of the lingo of particle physicists who are working on it every day, we draw squiggly lines and little diagrams, but it's supposed to encode the fact that when we exchange a photon between us 2 electrons, this represents his path when he chucks the ball, and this represents my path when I catch it. The interactions between us happened at a particular point. In string theory, when we're chucking a string between us, this is his trajectory as an ice skater, this is my trajectory as an ice skater, it's smooth. There's no particular point where the interaction happens. You can see that it's smoothed out over a particular part of space. Instead of happening at a mathematical point, it happens spread out. And the spreading outing is one of the fundamental reasons why string theory is a well-behaved theory of quantum gravity as compared to Einstein's theory, which isn't. Okay, so strings interact by smoothly splitting or joining, and this is just a picture of it. By the way, if you would cut this diagram in half and then rotate to put your ear on the floor, you would have what's called the pair of pants diagram. Again, theoretical physicists are not awfully imaginative about naming things. So next slide. Now there's one other fundamental reason, and again the slide is a bit busy, so just listen as if you're looking at the same time. We've explained that because strings are spread out, that smoothens out the interactions between things and gives us a chance to have a consistent quantum theory of gravity. There's another reason why strings are better behaved than point-like particles, and that is because they're extended objects. They're softer. They're not as pointy as particles are. After all, particles are just points. So one of the things that particle quantum mechanics tells you is if you have higher momentum, like you go faster, you get a shorter quantum wavelength. And this is such that if you go even faster, you can compress your wavelength quite a bit. And why this is useful is if you have a very short wavelength, you become sensitive to small-scale physics. As an analogy, consider in the kitchen, you've got a pile of sesame seeds on the bench. And suppose you wanted to pick them up. Now, if you took a giant pair of tongs, salad server tongs, for example, they're very big and clumsy, and it's very difficult to pick up individual sesame seeds. That would be like having a great big quantum wavelength while trying to uncover the structure of, subatomic particles. On the other hand, suppose I took a pair of tweezers instead of a pair of great big kitchen tongs. Because the tweezers have very pointy points, they're very sensitive to small-scale physics, and we can easily pick up and manipulate individual sesame seeds with the tweezers, whereas we couldn't do it with those gigantic tongs. So that's just part of the story of quantum physics, that if you want to be able to be sensitive down to smaller scales, you want to be able to pick up the sesame seeds, you need to whiz something along at a very fast speed so that you get its wavelength down nice and small. This is actually how an electron microscope works. The way that those electrons which probe the thing that you're looking at in the microscope, the way that you can get down to very small distance scales and actually see the atoms and the molecules is by accelerating those electrons to go really frickin' fast so that when they whack into the thing, they can dig deeply in and see what's happening there. So in fact, that's very much related to how an electron microscope works. So basically, it means that if you've got more money, you can make things go faster and you have better resolution. So the more money, the better. Now, string resolution follows the same path for a little while. If you keep trying to crank up the energy of a string, at first it will start becoming more and more sensitive to small-scale physics. And then there's a funny thing that happens that also is one of the other reasons why string theory is such a well-behaved theory of quantum gravity. And that is that if you continue to crank up the energy of your little probe string, let's suppose that I'm trying to uncover, if you can just hold this for me, sir. Let's suppose I'm trying to uncover something that's going on here, and I'm trying to fire little strings at it to see what's happening here. So, I try to make them go faster to be sensitive to the little ripples on the surface of this thingy. Thank you very much. So what you discover is if you crank up the energy too high, then the string itself starts to get fatter. And the resolution accordingly gets worse. And why this happens is a string has a certain tension to it. When you tune your guitar, you change the amount that the pegs pull on the string. That changes the tension, and it changes the pitch of the musical note. Similarly, if you've got a tension for your little string, your open string or your closed string, and at some point, if you pump too much energy into the string, it gets fatter, floppier. And that's why the resolution for the string gets worse if you crank the energy up too high. So there's obviously a law of diminishing returns. You crank up the energy to a point in string theory, and you learn more information. If you keep going and just throw more money at the problem, nothing much interesting happens. So the fact that there's a minimum distance to which string theory is sensitive is one of the fundamental reasons why it's a well-behaved theory of quantum gravity. There may be no physical meaning to shorter distances than that. Maybe the buck really does stop at string theory. Okay, next slide. I'm almost finished. Are we actually still okay with the 1 hour for the video? Okay. Did you say 10 more hours? I'm not going to go for that long. Maybe 10 minutes at the absolute outside, but more like 5 probably. I can come back to this slide if anybody cares. It's probably the most mathematical slide in the whole thing, even though I did promise I wasn't going to write an equation. I guess I snuck one in there by accident. Oh, look, there's another equation. Shoot, I really messed up. So at any rate, there's one of the beautiful things about string theory is that it's actually kind of hard. The math requires you to do an entire undergraduate degree in physics and then take some graduate courses before you can start learning string theory. You have to learn both Einstein's general relativity and the whole mechanics of quantum field theory, which is the story of taking quantum physics, putting it together with special relativity, and understanding all those quarks and leptons and the rest of the subatomic zoo. So what you're getting here is a description of things that you will never hear about in your undergraduate degree if you're a physicist. You'll only hear about in graduate school, but no math. Okay, so all I'll say from this slide is that the quantum physics of strings is a bit involved. You dig in and you try to make it all work, and you discover that there's this most amazing thing that comes out, is that it doesn't work in any arbitrary dimension of space-time. It turns out that you have to have 10 dimensions of space-time for a superstring, or 26 dimensions of space-time for what's called a bosonic string. And so string theory in particular predicts that there are more dimensions of space-time than the ones that we see. There were people who actually incorporated this idea of having extra dimensions of space-time over 80 years ago. People with the name of Kaluza and Klein. They invented the idea of having extra dimensions in physics, and nobody really paid any attention for like 80 years. Until string theorists came along and said, well, you know, it's kind of embarrassing, but we've worked out the quantum physics of strings, and it's not consistent in 3 dimensions of space and 1 dimension of time. It's consistent in 9 dimensions of space and 1 dimension of time. So there must be 6 more dimensions of space that we can't see at the moment that are hidden away somewhere. Where the hell are they? So string theory isn't the only theory that talks about extra dimensions. There is a lot of physics beyond the standard model, that particle zoo diagram that I drew, where people have invented the wildest, wackiest ideas for models of how the universe works in a mathematical sense. But string theory is new in requiring more dimensions for consistency. So that's a prediction that there are extra dimensions of space. The million-dollar question is, are they big enough that we can ever see them in the lab? Or find evidence left over, perhaps, in what we see in the cosmic microwave background radiation? So, back please. Let's imagine that this is supposed to be a model of physics with an extra dimension. And because I can't draw 4 dimensions on a page, I can't even draw 3 dimensions on a page. I can't draw. So I pinched somebody else's picture of a telephone wire with a little ant on it. And what I'm going to ask you to imagine is that the extended direction, the long direction of the telephone wire, is like our big dimensions of space, side to side, back and forth, up and down. Imagine that I just compress all those 3 into a single direction to make it easy to see on a piece of paper. So these big dimensions are huge. As far as we know, they're infinite. They stretch to the edges of the universe. But look and see that if you've got the telephone wire, there's another coiled up dimension that is perpendicular to the other one. If you were a big ant, you could only walk in one direction, the extended directions. The curled up direction is so small, it goes unnoticed. It's a similar sort of phenomenon that if I personally am looking at a telephone wire that's, 3 blocks away, I can't tell that it has 2 dimensions to it. All I see is the long direction. As far as I'm concerned, it might be just a line. But if I were to get up close, or I use, binoculars or, put my glasses on, then I can resolve the fact that it has an extra direction. So if you were a very, very small ant, only about the size of one of the dots on this picture, then the small direction and the big direction look pretty much the same to you. So that's how, if you have an extra dimension of space, if you're too big, like us, you might not be able to see it. Whereas if you're really teeny tiny, or you could dig very deep down to very teeny tiny distances by whizzing stuff around inside a particle collider, then you might be able to unlock the physics of the extra dimension. Now, there's something that's extremely important about extra dimensions that you have to know. And this is even something that someone as famous as Sir Roger Penrose has screwed up. For example, I was at a conference which was the 60th birthday celebration conference for Stephen Hawking back in 2001. Roger Penrose got up and gave a talk about how string theory was BS because of some stuff he didn't understand about extra dimensions. He failed to realize that in quantum mechanics, there's a very fundamental thing that says if you excite physics around an extra dimension, if you've got momentum in an extra dimension, you have to fit an integer number of quantum wavelengths around that extra dimension, otherwise the wave will cancel itself out. And the physical consequence of that little piece of mathematics is that there's an energy toll that you have to pay to go into an extra dimension. So you and I cannot tickle an extra dimension by poking our toe into it, because there's a minimum amount of energy that you have to pay in order to be able to go and explore the extra dimension. That's why we haven't seen it so far. It could be, however, that the energy required to open up an extra dimension might be accessible inside the Large Hadron Collider. So this is why people talk about extra dimensions being seen inside a particle accelerator. What they really mean is you'll see physics happening in our dimensions, and all of a sudden stuff will go missing. And we'll say, did we fail? Did we fail to calibrate our detector correctly, or did that really just disappear, that particle? And if it just disappeared, we would have to conclude that it went somewhere else, which must be into the extra dimension. So people are putting into the computers that are going to be running the sifting through all the data that comes out of the LHC to look for physics of the extra dimension. State-of-the-art experiments done at particle accelerators and on tabletop experiments tell us that if there's a universal extra dimension, that's the kind of extra dimension into which everybody can go, gravitons, photons, electrons, you and me, then they must be very, very small at about 0.01 Fermi. That's getting down to about attometer size, which is 1/1 of a meter. Really, really, really frickin' tiny. However, there are other kinds of dimensions that arise in string theory called gravity-only extra dimensions, and they're very unfair. They're not democratic. Only gravitons can go into the extra dimension for these guys. You and I can't go in. Electrons can't go in. Photons can't go in. We can't even shine a torch into the extra dimension to have a look. We can only send gravitons. And because gravity is such a weak force in our universe today, that the limits on how big that extra dimension could be are quite weak. And in fact, we know that the gravity-only extra dimensions must be smaller than about 0.15 millimeters. Now that sounds ridiculous, doesn't it? I'm standing here and saying that 150 microns across, there could be an extra dimension everywhere in our space that we don't know about. And why haven't we seen it? Well, we can't poke it with our finger. We can't shine light into it. Only gravitons can go into that extra dimension, which is why we haven't seen it, because gravity is a very weak force. So this is why I can credibly stand here and say that this is the limit on the size of a gravity-only extra dimension, because people have actually looked and haven't found them yet, but because gravity is so weak, we've got a relatively bad limit on how small that thing could be. Next slide. I just want to finish with one of the more complicated slides. There's just two more to say. Strings aren't the only extended objects in string theory. I just wanted to introduce the word that there's a thing called a D-brane. This is a place where an open string has to end. So you can see a little open string. It has one endpoint on the brane and the other endpoint on the brane. It's kind of like its feet are stuck on the surface of the Earth, like it can't lift one of its feet up, but it can move around on the surface of the brane. So the body of the open string can be doing anything it likes, but its feet have to be stuck on the brane. And so by knowing about how open strings behave, how they oscillate, how the mechanics of open strings work, we can work out the dynamics of D-branes. And these things were not discovered until 1995-7 or so. So we've only known about them for 10 or 15 years. D-branes gravitate. By the way, brane is short for membrane. We're too lazy to say demembrane all the time, so we just say D-brane. We're lazy. Branes, because they're extended objects, can wrap around stuff. They also gravitate, and they even have some very interesting things called gauge fields living on the brane. And because of these properties of branes, that they can talk to closed strings that are messing around in a place called the bulk, they can interact with open strings whose feet are stuck to the brane. There's a whole load of immensely interesting stuff that you can construct here. There are amazing physical equivalences that appear between distinct physical systems. This is like accidentally stumbling on an exact dictionary between two different languages. You and I both know, if we speak more than one language, that there are some concepts, for example, in Maori, that are not available in English. And there are some concepts in English that are not really available in Maori. So that's a generic situation for languages, that we don't have an exact one-to-one dictionary between each of the words and the concepts in the language. A duality in physics is like that it's a surprising circumstance where you discover that every word in one dictionary has an analog in the other dictionary. And finding the dictionary between them is something that keeps us busy and keeps us employed and off the streets and not bothering you giving talks at CFI. So let me just end up with my final slide. Maybe it's my second to final slide. Because of these branes, there could be very weird possible new ideas for how the universe came to be. For instance, suppose we live on a brane. This is you. It's on a slice in a bigger dimensional universe. If you like, you can think of it as like an infinite-sized piece of toast inside your kitchen. Then suppose that there's another piece of toast somewhere else in the kitchen parallel to yours. This is really crazy, right? But this is the kind of stuff we dream up, not just when we're at the pub. We're perfectly sober when we dream up these kind of theories. But, suppose that they were in relative motion and the red piece of toast banged into the green piece of toast. Just by accident. They happened to be just moseying around the universe and happened to find each other and go wham! Well, that collision would be very sudden, and it would all of a sudden dump a humongous amount of energy into our brane, onto our piece of toast, because we just got whacked by a giant red piece of toast. So this is a lot like what would happen if, a red car would crash into a green car, releasing a heck of a lot of energy and a whole load of debris in the consequence. So this is an idea for how the Big Bang might have originated. And words that go along with descriptions like this are called like the ekpyrotic universe and other such abominations. This is a different concept from the many worlds interpretation of quantum mechanics, and it's also a different idea from parallel universes. But the idea that we might live on a brane, a three-dimensional world that lives in a bigger dimensional universe, opens up a humongous panoply of new options for what the ultimate fate of the universe might be, or indeed how the universe came to be in the first place. So let me just end with a meditation about cosmology. Now, unlike particle experiment, the cosmos is a one-shot experiment. We can't just ask God to go and press a button and watch the Big Bang again. This limitation that there's only been one experiment for the origination of the cosmos, in other words, the one that we see and the one that we live in, that's a limitation to how much we can eventually know about how the universe works, and it's called cosmic variance. So this is part of what I was getting at in a very small part of the description of my talk, that there are fundamental limits to what we can know about the universe that arise just from thinking very deeply about it and seeing what we see out there and putting it together with the math that we developed, the simulations on the computers, and using it to understand the structure of the universe. Further, trying to apply quantum probability ideas to the entire universe to say that there's a probability to create a new universe and so forth, that poses some extremely deep conceptual challenges that no one has yet solved. Some people think that string theory will eventually be understood well enough to uniquely predict our universe. The idea is, well, once we're smart enough to figure all this stuff out, to work out all of the consequences and to, explore it all, and once we're, 50 years smarter than we are now, maybe we'll eventually be able to understand everything, and we will discover that the only solution to all of those beautiful equations is our universe. That's perhaps what the prevailing view was like maybe 20 years ago in the field. However, most practicing string theorists today think along what you might call less arrogant lines. I like to call this idea that string theory uniquely predicts our universe, perhaps at some point in the future, the cosmic arrogance hypothesis. It's not arrogant because of what we're trying to do. It's arrogant to assume that we're special in the universe, or maybe in some meta-universe. I mean, we're just a few, there's 100 billion galaxies in the universe. There's 100 billion stars in every galaxy. Our star isn't particularly special. Yes, we have a planet that has liquid water and a lot of other beautiful things. Little interjection. How many of you know that only hydrogen and helium and a teeny bit of lithium was made in the Big Bang? Awesome. Every other element in the universe, from beryllium on up in the periodic table, was cooked inside supernova explosions, which is what happens when stars that are a bit heavier than our sun, but not heavy enough to make black holes, collapse in on themselves after they run out of gas and make a big explosion. So literally, all of the complex atoms in our bodies are made of star stuff. Seriously. And none of this has anything to do with string theory per se. I mean, you would have known this even if you didn't bother thinking about how to unify gravity with quantum mechanics. So this is a really beautiful, beautiful idea that we live in this huge, awesome universe that's 13.7 billion years old. There's 3 Kelvin cosmic microwave background radiation everywhere. There's galaxies, there's stars. The expansion of the universe isn't too big so that the universe expanded before galaxies could form. There's a lot of kind of cosmic accidents that had to happen in order for us to be able to be here, to sit here with the complex molecules in our bodies and brains studying all this rubbish. So, it's much more likely that our universe was probably a cosmic accident. There could be other very foreign universes living far away from us, so far we can never communicate with them, that might have different particle spectra, different number of big dimensions, different strengths of forces. They might have no forces. There might not even be any gravity in those universes. String theory has what's called a huge landscape of possible universes, a truly humongous set of possibilities that plagues us because it's a bit of an embarrassment of riches. We have too many possible models for how the universe might be. It would be nice to be able to say, well, ours was the only one there could have been. But we're not there yet. We can't say that with any degree of confidence. By the way, if you're interested in other approaches to marrying together Einstein's general relativity theory of gravity with quantum physics, there are other approaches on the market called loop quantum gravity. But, if string theory has a big landscape problem, loop quantum gravity is even huger because it doesn't have any quantum mechanical consistency conditions like string theory does. That's one of the major reasons, and the fact that loop quantum gravity doesn't even obey the correspondence principle is the reason why I don't work on it. But if one one day tomorrow they were able to show that this loop quantum gravity is actually a quantum theory of our gravity as compared to some other wacko theory of gravity, then I would sit down and learn it. And so would everybody, including all the Nobel Prize winners who currently poo-poo it. If they could show that one thing, that it actually is a theory of gravity, then we would all be working on that instead of string theory, most likely. But to get back to the main message, humanity and our planet and star are just specks in a vast universe, and we're cosmically insignificant. Being reminded of this every day when you study this topic is very humbling. So, humbly, I thank you for your time and willing to take questions now.
Hi. You mentioned towards the beginning that scientists were worried about black holes because it represented an epic fail because they would lose information. And then a little bit later, or considerably later, you said that there's an energy penalty to unfold one of the small dimensions. Wouldn't that represent a similar loss of information if a whole bunch of our energy, as you described it, disappeared into a folded up dimension? And is this an epic fail, or how do you get around that?
That's a great question. So I think the honest answer is to say that we understand how it works. The way that it manifests itself is that we look at, for the fact that you have to pay a certain energy toll or a momentum toll to be able to go into the extra dimension. It means that if you would have one particle going into the extra dimension with a certain amount of momentum, there would have to be another one going in the opposite direction. Otherwise, they wouldn't add up to be no momentum in the original direction which they had originally. What I'm trying to say in a long-winded way is that we apply the law of conservation of energy and the law of conservation of momentum, but we do it including all of the dimensions. If we failed, what would be an epic fail would be to say it's the four-dimensional energy that's conserved, rather than all of them. So if we insist on applying these sacrosanct principles of conservation of certain properties that we know and love, like energy, you can't create or destroy energy, it just goes from one form to another, that kind of idea. If you apply that, taking into account the energy toll that particles would have to have if they went into an extra dimension, it all works out consistently. So it would be a different kind of a fail than the epic fail of general relativity at short distance. So there's as there's a hierarchy of wrong, there's a hierarchy of fail in building theories. So what we try to do is start with any approximation, and then we discover that it fails epically somehow, and then we try to do better, we keep iterating to try to make a better and better theory. And maybe we'll never get the correct, truthful theory, but as long as we do the best approximation we possibly can, given the limits of our human imagination, then that should be as far as we could go. I hope that begins to answer your question. But you're absolutely right that you have to account for everything. You can't just focus myopically on our world and forget about the other world.
Hi. I was astonished when you were speaking about the composition of the universe that most of the material is stuff that we can't sense directly.
We only sense it from its gravity.
Right.
It doesn't shine, so we don't see it in our telescopes.
I see. So, okay. So I inferred from that the way we know it is by applying a model of gravity. And so my question is actually, you talked about different models of gravity. Do they predict different amounts of missing stuff? And can the amount of missing stuff that they predict, so the stuff we don't sense, can the size of that be used as a test of the model?
You bet. And that's exactly why we care. That's excellent point. And that's, basically the origin of the enterprise of modern early universe cosmology. What we're trying to do is to what you might refer to technically as an inverse scattering problem. You see the universe in front of you now, and you want to know what models could have given rise to our universe now with that composition, given certain assumptions about the way gravity works. So indeed, you're exactly right that making different models for how gravity works, some people, for example, have worked on gravity models where the speed of light is different from the speed of gravity. Einstein built the assumption that those two speeds were the same into his general relativity theory. So you can't test that assumption unless you move outside of that rubric to a theory which does have different speeds, and then you check If there's a speed differential, how much does that change the composition of dark matter? How much does it alter this, that, and the next thing? It would change the clumpiness of cosmic microwave background radiation on the sky. And that's exactly what we're trying to do, to use information about the universe, what we can see, using that look back in time thing with the finite speed of light and using what we see right today. That's exactly, what modern cosmos...
Stuff,
yeah.
Okay.
Yeah, exactly.
According to what I have read, after some decades of work by a lot of very, very smart people, string theory has not yet come up with a single falsifiable prediction.
That's actually profoundly wrong, and whoever wrote that should be smacked around the head.
Philip Anderson is a...
Yeah, Phil Anderson is a well-known long-term critic of string theory, and he was one of the people who testified to Congress and got the superconducting supercollider cancelled in the United States. By the way, the LHC machine that's about to go online in near Geneva, it's a lot smaller than what the SSC would have been if it had been built. So Phil Anderson has an agenda when he makes this criticism, which is that he thinks that his field, superconductivity research, doesn't have enough good, bright people working in it. And one of his single-handed goals in speaking ill of string theory generally is to get more people to go work with his stuff. So, take it for what it's worth. We're humans just like the rest of us. But, I want to speak to you the fact that you said that there are no falsifiable predictions of string theory. That's absolutely, fundamentally, completely, utterly wrong. And in fact, there was a beautiful paper that was published, for example, in the Physical Review just a few years ago by Jacques Dissler, who's a scientist who works in the same group as Steven Weinberg at the University of Texas, Austin, where they showed very explicitly that there are several measurements that you can already do that would falsify string theory. So that's profoundly wrong.
Okay, thanks.
It's very technical, the reason why, and I don't want to dismiss the question. It's a perfectly reasonable question. After all, one of the responsibilities of science, I think, is to ask the impertinent questions. Please come up to the mic so that other people can hear.
So in that case, can you give an example of a physical phenomenon that cannot be explained without string theory, and string theory explains
gravity.
it perfectly?
Quantum gravity? How about the entropy of black holes? What's the standard of proof that you would require for the answer to be satisfactory?
Well, I tell you...
Please answer the question.
I'm engineer more than physicist. For example, when general relativity came in, there were a few phenomena like the shift of stars in a solar eclipse, the movement of the perihelion of Mercury, and many others that I don't need to go into all of them.
Well, one of the big examples is the entropy of black holes. There's no understanding of that presently without string theory. So, I don't know whether that satisfies you. It's a theoretical computation at the moment.
Well, it's theoretical.
Right, but please answer the question. What standard of proof would you like?
Did we measure it? Do we have a black hole to measure the entropy?
Yes, we have astrophysical black holes out there, but they're very large, and
I think we cannot measure the Hawking radiation.
Well, okay, so don't bother studying string theory. Why did you bother to come to the talk if you think it's a waste of time?
I want to know about the string theory
right,
more.
So these are the reasons I've given you as best I can and as accessible a language as I possibly could. It's a very technical subject, which we, as I said, we don't normally teach to undergraduates, and I'm taking a risk by trying to teach it to lay people here. But what I tried to lay out for you were all the reasons why particle theory was not sufficient to explain the universe. So, it might be able to explain for us why we have 3 generations. Why do we have 6 quarks? Why do we have 6 leptons? Why are there 3 large dimensions of space? These are all the kinds of questions that string theory is attempting to answer. But until we have more data, we won't be able to rule out theories. So that's why so much of the future of the field hinges on what's found at the LHC. What we want to do in this whole enterprise is to push mathematical modeling, computational simulation, and experimental measurement to the very limits of what we can do. And if we can't go any further, we'll figure that out. And the field will peter out, and we'll all go and work on something else. Probably, maybe superconductivity, or who knows. But one of the ultimate ironies of the story is by using systems of large numbers of D-branes with one another, physicists, string theorists, not condensed matter physicists, have recently come up with possible ways of understanding superconductivity by using, of all things, black hole systems. That would be the ultimate joke on Phil Anderson, I think.
It would be interesting, really. Thank you.
When do we have to be out of the room? It's like 20 minutes from now. I'll take maybe 5, well, maybe I'll try and take all these questions, we'll see.
Hi, I have a question. String theory and loop quantum gravity is very close, right?
Well, they both purport to be theories of quantum gravity, correct?
Yeah, so, but I don't understand why Lee Smolin don't against string theory.
Well, neither do I, and I wish he would shut up. Is it, so you don't want to hear my professional opinion about what he says in public. It's not very nice, so I'm not going to show it. What I will say, some people have a very balanced personality. They have chips on both shoulders. My thesis advisor, Lenny Susskind, who's a far better theoretical physicist than Lee is, and I know for a fact that I'm never going to be even 1/100th of the kind of physicist that my advisor was. No matter what happens in my future, I'm not that smart, and I don't mind. I'll make my little contribution as I can, and that's perfectly fine. But, Smolin is not the same greatness of physicist. And Lenny Susskind debated Lee Smolin on the Edge website, egged on by the person who runs it and everything for, trying to actually hash out this issue. What is true and what is false about claims in the public sphere about what string theory and loop quantum gravity can do. And even Lenny couldn't convince him to change his opinions. He's got a certain deafness to listening to some other kinds of physicists. And, I think that's partly because of his history, that he's worked on less popular topics, and you have to have a fairly thick skin to choose to work on something which isn't the prevailing opinion about something. But don't let me confuse you about one very important thing. It's absolutely critical in science that we have an ecology of styles, an ecology of thought processes, an ecology of theories. Even though string theory probably has at least 50 times more people working on it than loop quantum gravity, it could well be that loop quantum gravity, or something we haven't even investigated yet, holds the key to understanding. So it's critical that we have people that work on loop quantum gravity. Maybe the way that it will turn out is that they will discover that there are only certain theories that work and they have certain consistency conditions, and maybe those will turn out to be the same quantum consistency conditions as string theories, who knows? In order for them to be able to produce the Newtonian limit in the theory, which is the hardest thing for loop quantum gravity to do, to show that it's connected to classical gravity. They actually just propose that quantum physics applied to general relativity can be done in such a way that it's consistent. There's no evidence whatsoever that this is the case, but they make an assumption and proceed from there. So,
Okay. Can I ask more questions? Is there any new...
Perhaps you could go to the back and let the other people ask a question, and then if we have time, we could come back. Is that fair, do you think? Please go ahead.
I guess you're about to tell me why I'm really long on this question, too, regarding Lee Smolin, but I guess 2 questions. What do you think of his book? Maybe you've already answered that, according to your opinion about him.
Yeah, my opinion is not very high.
Okay.
I mean, he writes beautifully.
Okay.
But some of the things that he says are exaggerations at best, and that's a charitable phrase for it. Sometimes he just outright lies.
Yeah, one of his claims is that string theory still fails to make any contact with nature. I guess that's probably not true as well. And is the LHC the next step towards that, or has that already happened in experiments that we don't know about yet?
String theory, like every other theory of what happens beyond the standard model, in other words, what we already know and love and we think we understand, any theory that talks about what has yet been undiscovered is on shaky ground by very definition. And loop quantum gravity is in exactly the same position as in any other kind of approach to understanding the physics. So, let's encourage a healthy ecology of styles. I think people shouldn't make out an approach to be bigger than it really is. And I think that's something that Lee could learn a little bit of, is just to try to be a bit less, PR-ish about the way things work. He does write very beautifully, but I think that the science isn't quite commensurate with the reputation.
Okay, thank you.
Shit, did I just say that on video?
Hi, I was wondering if there's like a
Well, I believe it, and I would defend it in a scientific context, so it's not a lie.
So is there like a really easy way to kind of get across how the mathematics for like classical physics and quantum physics and then string theory relate? Like, is it sort of a modular thing where the term drops out and then there's an equivalency?
Well, string theory is a quantum theory. So, it's a quantum theory of everything in it, including open strings, closed strings, gauge particles, electrons, gravitons, and everybody. So it's by definition not a classical theory. Classical means not quantum. So it means talking about the macroscopic realm while remaining ignorant of what happens at very short distance scales.
So, but like if you mathematically slice parts of it off, then does it collapse down to the same equation, I guess?
I'm not sure I quite understand the question. Could you give me an example, perhaps?
Okay, well, say there's like a classical equation for how gravity works. And
yes,
then
that
you have
would be
quantum.
Einstein's equations of general relativity.
Right,
Okay.
right. So, and then you have the quantum string theory equation. So if you take...
those two equations are differ, but the really important thing is something called the correspondence principle. That if you take any quantum mechanical theory and you ask what happens at macroscopic distance scales, you should get back what you know classically. This microphone is now dead?
No, it's still working.
Oh, still working? Okay.
Just quieter.
I see. So the true answer to your question is that the quantum animal is bigger, and it should match on smoothly back to the classical equations that we know and love from macroscopic physics in the limit that you're talking about large distance scales. So that's called the correspondence principle, and it's an absolutely critical feature of any sensible quantum theory of anything, that once you take the quantum physics and take the large long wavelength limit, take the macroscopic limit of those equations, you should get back the classical equations. And if you don't, you've done something wrong.
So it has like an additional module kind of thing.
Yeah, I would say it's kind of like a smooth limit.
All right, thank you.
And technically it's actually the limit in which Planck's constant, something called h bar, which is very small in human-sized units, strictly goes to 0. So.
Thanks.
Do we have time for one brief final question? Oh, okay. So just make it brief if you can.
I'd like to know, is there any new development for M-theory recent years?
So M-theory is related to these 5 kinds of superstring theories and an extra dimension of physics called 11-dimensional physics. Yes, there have been actually some quite important advances in understanding M-theory in the last year or two. They go by the name of the ABJM correspondence, blah, blah, blah. It all has to do with this notion of branes and the fact that if you stack up a whole bunch of D-branes on top of one another, you develop what's called a large N quantum field theory living on the branes, and you've got gravity living in the bulk. And by taking a very special limit of this system, you can derive a duality, and that's called idea CFT. It's an extremely important idea. It was invented by Juan Maldacena, who was actually a graduate student at Princeton when I was working with him as a postdoc. It was one of the singular experiences of my postdoc career to discover that this graduate student I was working on was way smarter than me. So, it happens, right? But don't be upset. Make the contribution where you can. There's many new developments. They're usually reported every year at the Strings Conference. For instance, Strings 2010 is going to be held in Texas, College Station at A&M, go Aggies, whatever. Go Canada. By the way, did you guys notice that all but 3 of the medals and 1 pairs medal were won by women for Canada? Go girls! Anyway, so yes, there have been new developments, but it's pretty difficult to describe them in a very brief way.
Okay. Thank you.
So thank you everybody for the awesome questions, and thank you for listening.
Centre for Inquiry, Canada's premier venue for secular humanists, atheists, skeptics, and free thinkers.
This event was hosted by the Centre for Inquiry Canada, an educational charity promoting science, reason, secularism, and free inquiry. CFI Canada coordinates branches and campus groups across the country, runs a public education series, provides secular community services, incorporates cutting-edge multimedia such as blogs, podcasts, and YouTube, and is a regular voice in the press presenting a secular humanist, atheist, and skeptical perspective. Visit us at www.cficanada.ca and contact us at info@cficanada.ca.